Welcome to sum and products of roots, also known as zeros. The zeros or roots of a quadratic. So let's just go over some of our information that we've done in the past. So we know that the quadratic can be written in the form of ax squared plus bx plus c. And if we have roots of alpha and beta, then we could factorize that to x minus alpha, x minus beta as our two brackets that they would come from. So expanding the right-hand side and equating our coefficients. So when you expand x minus alpha, x minus beta, you get x squared minus alpha plus beta x plus alpha beta. The left-hand side, let's make the coefficient of x squared the same. So divide ax squared plus bx plus c, divide everything by a. And you'll notice that our x squareds are the same. So that means the coefficients of x, which is b over a, and minus alpha plus beta have to equal each other, and our other coefficients, the constants, c over a has to equal to alpha beta. So the sum of the roots is equal to minus the b over a, and the product of the roots is c over a. So when we use these, we can write them out as the sum of the roots is minus b over a, and the product of the roots is c over a. Now, a version of this is on the actual formula sheet. It's under cubics, but we can narrow it down to quadratics as well. So here's a simple one. For the quadratic, p of x equals 2x squared plus 10x plus 8, we're going to show that x equals minus 1 is a 0, just like using factor theorem. Then we're going to use the sum of the roots to find the other 0, and we'll use the product of the roots to show that it's the exact same x value, whether you use the sum of or the product. So subbing in minus 1, you can see p of minus 1 equals to 0. So using the sum of the roots, so if we let alpha equal to minus 1, because that's one of the roots, then minus 1 plus beta is equal to, and if you look at your quadratic, b is 10 and a is 2. So you get minus 1 plus beta equals minus 10 on 2 or minus 5, add the 1, and the other root is minus 4. Let's do the same but using the product. So minus 1 times beta, so because alpha beta equals c on a, so minus 1 times beta is equal to 8 on 2, divided by the minus 1, beta equals minus 4. So if we let alpha and beta equal to the roots of that quadratic, so we're not actually going to find in this case what alpha and beta are, we're just going to form a set of terms. So just using our rules. So first one's alpha plus beta, and we know that that's minus b on a. Alpha beta is c on a. And for parts C and D, we're going to have to manipulate them into using alpha plus beta and alpha beta. So for this quadratic, A is 1, B is 8, and C is 24. So for part A, which is alpha plus beta is minus b on a, so that's minus 8 on 1, or just minus 8. The product is c on a, so c is 24, a is 1, so 24 on 1, so the product is 24. 1 on alpha plus 1 on beta. Well, we also know that in part A we found what alpha plus beta was, and part B we found what alpha beta was. So if we get a common denominator, 1 on alpha plus 1 on beta gives us alpha plus beta on the top of alpha beta. That changes to minus 8 on 24, or minus a third. And for the fourth example, alpha squared plus beta squared. So let's look at alpha plus beta squared, because we know that's where alpha squared plus beta squared appears. But if we do the expansion of alpha plus beta all squared, you get alpha squared plus 2 alpha beta plus beta squared. Now on the right hand side, if I want to leave alpha squared plus beta squared by itself, I'd minus 2 alpha beta from both sides. So therefore alpha squared plus beta squared is alpha plus beta all squared minus 2 alpha beta. Subbing in what we found in part A and B, alpha squared plus beta squared is 16. Now for the sum and products of zeros of a cubic, this is on your formula sheet. So the sum of the roots individually is minus b on a. So that's every time. The sum of the roots individually will always be minus b on a. The sum of the product of the pairs of the roots will always be c on a. And the product of the roots 3 at a time, or in this case, since we've only got 3 roots, alpha, beta, and gamma, that's minus d on a. If we were looking at a quartic, not that this is on your formula sheet, but we could be asked, the sum of the roots is minus b on a. So we've got alpha, beta, gamma, and delta as our roots. The sum of the products of pairs, so multiplying all the pairs together, alpha, beta, alpha, gamma, alpha, delta, beta, delta, gamma, delta. So all of those pairs is always going to get you C on A. The sum of the product of the triple roots, so the addition of all the 3 roots together, alpha, beta, delta, alpha, gamma, delta, beta, gamma, delta. So they're the 3 at a time, that's always minus D on A. And the products of the roots, or this case 4 of them, is now E on A. So you'll see it goes minus B on A, C on A, minus D on A, E on A. So here's an example. We've got alpha, beta, and gamma are the roots of a cubic, where A is 2, B is 4, C is 8, and D is 24. Let's find the sum of the roots 2 at a time, and then something that uses those all over. So for this, I mentioned before what A, B, C, and D equal. Alpha plus beta plus gamma is minus the B value over A. Since B is 4 and A is 2, you get minus 4 on 2 or minus 2. The sum of them at 2 at a time is C on A. So that's 8 on 2, which is 4. And finally, 1 on alpha plus 1 on beta plus 1 on gamma. So when you do that, you get alpha, collect like terms, get a common denominator, alpha, beta, gamma. On top, you get, so the first one doesn't have beta, gamma, the second one doesn't have alpha, gamma, and the final one doesn't have alpha, beta. So on the top, you get the sum of the roots 2 at a time, which was 4. And on the bottom, you get the product of the roots, which is minus D on A, which is minus 12 in this case. So you get minus a third when you work that out. Thank you.